hours on Thursday, so I apologize if you need to see me and you can't come on Thursday's office hour. Just send me an email and we can arrange for a meeting. Another quick announcement: the project will be updated very soon. So within the next day or so, we'll have an updated project posted. But don't let that stop you from getting started, because you can do a lot of the simulations like noise and things like that without the linearity specs are what are going to mainly change. Okay. Questions or comments? Anything from Al?
There's no homework here that people can pick up, so in the class will be, I'm guessing, homework 5.
Yeah, if you're missing any homeworks, also look outside my door. I put the old homeworks there. All right, and homework is due today, as most of you know. All right, so let's start on this new topic. So oscillators are a pretty exciting topic to study, mainly because they're kind of different beasts from the other kinds of circuits that we've studied. In some ways, you might even say oscillators are alive, right? They're circuits that, you turn on the power and then they start basically doing something interesting, and they do it on their own. So there's no input signal, and yet there is an output signal. So they're very nonlinear circuits, for one thing. As we'll see, you can't build oscillators out of linear circuits. You definitely need some kind of nonlinearity. The other thing that's nice about oscillators is that they basically go against all the criteria that we have for amplifier design. So when you're designing amplifiers, you're spending all your time making sure that the loop gain is basically has the right phase shift, that you have negative feedback, that your poles are in the left half plane, that the system is stable. With oscillators, you do the opposite. You make the system purposely unstable. So it's your chance to be bad in some sense and have some fun. So I think you'll enjoy oscillators a lot. Let's start out by just defining what we mean by an oscillator. So an oscillator is a system where when you turn it on, basically with just DC power, you'll see the oscillation grow and then basically go into a steady state behavior with some very well defined period of oscillation, T. And we'll see that actually for any real oscillator, the period T, of course, which is inverse to the frequency, is not constant. It varies from cycle to cycle, but that variation is very small. So for all practical purposes, for the first 3 lectures, we're going to assume that there is no noise in our system, so that the oscillation is actually a fixed frequency. So what we're interested in is knowing the steady state behavior. So we want to know the steady state oscillation amplitude and frequency. Okay. And let's also note that oscillators are autonomous circuits. In other words, they don't need an input. They basically take their own output and generate a new input. So they're very different from all the driven circuits that we've studied so far. So let's say as opposed to driven circuits, where there's an explicit input pumping the circuit with a given frequency. So what's neat about an autonomous circuit, because there is no reference circuit driving it, that means that it determines its own period based on some kind of time reference, right? Internally, the circuit has to have some kind of time reference. And that means that the period of oscillation is determined by either an LC tank or a crystal or some other resonator. For instance, a cavity resonator, a dielectric resonator, or something that has intrinsically time as part of its characteristics. Okay. Questions? So, some important qualities about an oscillator. One is frequency stability, or equivalently phase stability, amplitude stability, Um, let's say the power consumption. Something that we'll talk about later is tuning range. And usually when we talk about tuning range, we're not talking about a simple oscillator, but we're talking about a VCO or an ICO, which is a voltage controlled oscillator, or perhaps a current controlled. And so the idea is that if we can somehow vary this frequency of oscillation with a control voltage, then we have what we call a controlled oscillator. Okay? And so what does it mean to have, let's say, amplitude stability? Let's focus in on amplitude stability for a moment. So by amplitude stability, I mean that let's imagine that our oscillator has been oscillating for a while at some fixed amplitude, and somehow I disturb my oscillator. Let's say, for instance, if I have an LC tank, let's say that I somehow place some extra charge on top of this capacitor during the oscillation cycle. For instance, I might have a current source that injects some extra charge onto that capacitor plate. That means that if I inject that charge, let's say at a maximum or minimum, what that does is it changes the amplitude of the oscillation, right? Q is equal to CV. I make Q larger, V goes up. So that means that this disturbance would cause the amplitude to grow. Okay? So at this moment in time, I inject charge onto cap. Equivalently, I could also inject current into this inductor, or magnetic flux into that inductor, and I would achieve the same kind of effect at a time of zero crossing. So I'm disturbing the amount of energy that is in this tank. Well, what happens is, because this amplifier, this oscillator is stable, we find that it actually will recover to basically the same value. Bad drawing. So basically, disturbance is rejected. In other words, internally the oscillator has an amplitude that it likes to oscillate at. And if I try to change that amplitude by disturbing it, it'll say, no, I like to oscillate at this given amplitude. So that's one nice property, amplitude stability. Unfortunately, oscillators do not have phase stability. In other words, if I now, instead of injecting this charge at the time where the amplitude is maximum, if I inject the charge when the amplitude is minimum, or doing a zero crossing, clearly that will change the phase of the oscillation. The oscillator has no way of rejecting that. There is no phase reference internal to the oscillator. There's only an amplitude reference. Okay? Now, if that seems a bit abstract at this point, we'll come back and talk about this later in the course. Okay? So the fact that there is no phase stability leads to what we call phase noise. Okay? And there's many ways of understanding phase noise. You can think of it as what I mentioned earlier, that the period of oscillation is actually not constant, that there's some jitter. In other words, the period changes in a random way. There's some fluctuation of the period. Another way to see phase noise is if you plot this, if you hook up your oscillator to a spectrum analyzer and let the spectrum analyzer basically average over many, many cycles. What would you expect to see? Well, if you had a perfect oscillator with a fixed frequency, you know its power spectrum would be a delta function. All the energy would be concentrated at one frequency, right? But for a real oscillator, what you see is a spectrum that looks like this. So there's energy at peak energy at F naught, the frequency of oscillation, but there's also energy at other frequencies. Okay? Now, if you have an LC oscillator, it's basically an LC tank with some energy regeneration mechanism because this LC tank has finite Q. So you might think that the shape of this spectrum is related to the shape of the tank impedance. In fact, nothing could be further from the truth. If you were to plot the tank impedance on the same scale, it might look something like this. In other words, if this were an LC tank, it would be a very, very high Q LC tank. Okay, is there a question in the back?
What about the windowing that the oscilloscope provides?
That's a very good question. We're assuming that this thing has been running for billions and billions of cycles, so the effect of the windowing is very, very small. And that's very easy to achieve because let's say it has a gigahertz frequency. That means 1 billion cycles per second. So if you just wait a few minutes, you've had so many cycles that there's no windowing effect. But if you're doing a simulation, certainly you don't want to wait, you know, a Google cycles, right? You will see the windowing effect. So, in fact, a lot of times I've seen people make this mistake. They'll take an FFT of the oscillator spectrum and they'll see something like this and they'll say, this is the phase noise. No, that's not the phase noise. That's the windowing effect that you bring up. To simulate the phase noise, you have to have noise in your circuit. And when you run a transient simulation, on most simulators, there is no noise. Well, there's round-off error, which manifests itself as noise, but there is no, you know, ignoring the round-off error, there's actually no noise in a transient simulation. So a transient simulation cannot pick up this phase noise. You have to do something more sophisticated. You can do a simulation where you actually introduce noise into your transient, but the number, because that noise has such a white spectrum, it would have to supply basically new data points very, very often, right? So if you're doing a transient simulation and you introduce a transient noise source, that transient noise source would have frequency components way out to terahertz, and so it would really slow down your simulation. Well, you could have, of course, you don't have to use it all the way out to terahertz, but you still need to have a pretty wideband noise source in order to get the phase noise effects that we're talking about. Okay? So the way we measure phase noise is, instead of plotting it like this, we plot it on a log-log scale. In fact, Al showed some phase noise plots during his talk the other day. So I would plot the carrier power, and this would be an offset, and it would maybe look like a line. You might actually find that there are multiple regions where the slope changes, and typically there will be a region where the power drops like 1 over f squared, and you would basically specify the phase noise at a given offset frequency, let's say 10 kilohertz. You might say that the phase noise, or the spectrum, drops by, let's say, 100 dBc per hertz at that particular offset point. Okay? Now we're going to have a whole lecture on phase noise, so we'll come back to this topic. Just so you're aware of it and the terminology, we'll spend plenty of time on phase noise itself. For the next 3 lectures, again, we're going to assume our system is deterministic, that there is no noise, there is no random noise source. Okay? So you might wonder, can I just build an oscillator out of an LC tank? Or for that matter, any resonator, a crystal. Okay? Well, no matter how good your LC tank is, and by good I mean no matter how high the quality factor is, if you put energy into the LC tank, it will dissipate, right? And so the spectrum will be a decaying exponential, and so it's not a stable oscillator. There is no amplitude stability. First of all, if I at some point inject more energy into the tank, I'll find that actually there is no amplitude stability. What happens is it just decays back down to 0. So no matter what I do, the poles of this system are in the left half plane. So this always decays. Okay? I can now try really hard to move the poles closer and closer to the j omega axis, right? But the closer they are to the axis, the higher the quality factor. Okay? So to give you some idea of how quickly this would die out if I had an LC tank, let's say the Q is 10. Let's say something you could achieve on chip. A Q of 10 roughly means there's the energy stored in this tank is 10 times larger than the energy lost per cycle. So within 10 cycles, almost all the energy is gone. So you might observe 10 of these cycles. Well, that's a pretty bad oscillator, right? Let's say you bought some expensive components and you put them off chip and you get a Q of 100. Well, again, that's pretty sad, right? 100 cycles won't last you even a second. Let's say you go out and build a mechanical resonator and it has a quality factor of 1,000,000. Okay? Still, that's only 1,000,000 cycles. You won't even see 1 second of a gigahertz oscillator, right? You'll see 0.1% of a second. So clearly, you can't build it from, we cannot build an oscillator with passive components alone. We need some active components. Because we need somehow to regenerate the energy of this tank. Okay? And you know, mathematically, the analogy is a pendulum or a spring on a mass, right? If you set a pendulum in motion, the nice thing about a pendulum is the period is determined by basically the length of the wire, right? That's great. You have a nice time reference. In fact, that was probably man's first time reference or people's first time reference. But that will also decay with time. So unless someone comes in and taps that every once in a while, that thing is going to die out. So that's the role of the active element. So one perspective to build an oscillator is to use feedback. So I'll call this the feedback perspective. And so the feedback perspective is I'm going to introduce an amplifier to regenerate the oscillation. What I'm going to do, I'm going to first of all represent the loss in my circuit with a resistor. Okay? And then I'm going to take the output of this tank, hook up an amplifier, and hook it up with positive feedback. So I'm going to take the output, invert the phase, because my amplifier is inverting, so that I have a positive feedback system. And so this is a regenerative system. You can think of it this way. If you have a noise voltage or disturbance at the output, it gets fed to the amplifier input, amplified, and it appears as a larger signal in phase with itself at the output. And that keeps going around and around. And so intuitively, you might guess that this circuit would actually start growing, right? The output amplitude would start growing, and it would ring because you have an LC tank here. So intuitively, you would expect the circuit to ring with an increasing amplitude until this amplifier compresses. Once the amplifier compresses, we know if the signals get large enough, the gain starts to drop. You can imagine that it might compress, and you might end up in a steady state situation. But that's just a guess, right? We haven't really proven that, and that's what we're going to do. So we can say that this is a regenerative system. So a noise voltage will cause ringing at increasing amplitude until the amplifier compresses. Okay. Now there's no guarantee that it's going to compress and stay steady. In fact, Al mentioned squegging a couple lectures back, where what you would see is the amplifier would reach a certain amplitude, it would compress to the point where it would just die. So then it would decrease in amplitude and go back down to 0, and then repeat again. So you can actually end up with a situation where you do not reach a steady state sinusoidal oscillation. You end up with two oscillations, a low frequency oscillation and a high frequency oscillation. Okay? So this is the negative feedback perspective. There's another perspective which is the negative resistance perspective. And the idea is extremely simple. The idea is as follows. You could say that if in steady state I reach a constant amplitude of oscillation, then whatever I hook up to this passive tank, this is my active network, it must be supplying energy to my tank. Because I know I'm losing energy to thermal heat through this resistor. And if something supplies energy to me, it looks like a negative resistance. So if I look into the terminals of this active network, no matter what it looks like, it should be a negative resistance. In other words, because they're in shunt here, I'll talk about conductance. The negative conductance looking into here perfectly compensates for the positive conductance here, so that overall the circuit looks lossless. Okay? So let's say that the negative conductance of the active network compensates for loss in LC tank. All right. Questions or comments you guys would like to make? So that means that if I go back to this circuit and if I look into this terminal, the output impedance of this device should be negative. Which is interesting. Okay. Now clearly that's not the real output impedance of the device, that's due to the feedback action. Okay. All right, so let's focus for now on the feedback approach, and probably next lecture we'll look at the negative resistance approach. And of course, we know that any feedback system that we have, let me draw it like this. Let's say I have a forward gain of A of S and a feedback factor which can be possibly frequency dependent. This is my input, this is my output. Okay? And we know that basically the closed loop transfer function for this system is A of S 1 plus A of S F of S. Okay? Now, when we designed amplifiers with feedback, what we tried to do was make sure that the feedback at all frequencies where there's gain had basically negative loop gain. What we want here is actually positive loop gain. We want regeneration. So let's see how that comes about. Let's look at an example. Let's say that we have an amplifier with a pole, basically A of S, A naught, 1 plus ST cubed. In other words, imagine you have an amplifier that has a pole at frequency 1 over tau, and we basically take 3 of them in cascade. So this is the transfer function of the cascade. And I want to see what happens when I apply feedback around the system. Okay? So if I do that, the closed loop gain is again A of S, 1 plus A of S times F. Let me assume that my feedback is frequency independent. Okay? So I get A naught 1 plus S tau cubed plus A naught F, if I just substitute for this transfer function. And I want to write this as 3 poles, 1 over S1, 1 minus S over S2, 1 minus S over S3. Okay? Clearly this is a cubic function and I can always factor it and find its 3 roots. So S1, 2, 3 are the complex poles of the system, of the closed looped amplifier. Okay? In this particular case, the math is pretty easy. We can just directly solve for these poles. So let's solve for these poles. I have 1 plus S tau cubed plus A naught of F is equal to 0 by definition. In other words, 1 plus S tau is minus A naught F cubic root. And I can write this as the cubic root of minus 1 times the cubic root of A naught F. And you'll recognize that A naught F is the loop gain at low frequency. David?
Yeah. Can you use a trans function to analyze a nonlinear system like oscillator?
Yeah, that's a very good question. Why are we using linear circuit theory to analyze an oscillator? Well, the good thing is that when you're looking at the stability of the system, you're looking at what happens if the oscillator is just sitting there, right, at some steady state, some quiescent point, and you inject a small noise voltage. There's some kind of disturbance. What happens to that disturbance? If the amplifier is stable, it'll reject that disturbance. It might excite transients into our system. The circuit might ring a little while, and then that goes away. If it's unstable, that will actually cause the system to regenerate and go into a steady state, potentially go into a steady state oscillation. Okay, that's a very good question. Okay, all right. So what's the what are the three roots of minus 1? Well, you know, it's just the unit circle intersected in 3 equal parts. So I get minus 1. I get e to the j 60 degrees and e to the minus j 60 degrees. Okay, and that means my poles are minus 1 minus A naught F cube root over tau. That's one of them. And the other 2 roots have a component e to the plus or minus j 60 degrees all over tau. Okay? So this is interesting. It tells me what my poles are as a function of the loop gain of the system. Okay? What I can do is I can make a root locus. In other words, I could plot pole locations as a function of the loop gain, which is A naught F, the DC loop gain of the system. Okay? And what you find is basically just plugging these guys into this equation. First of all, let me assume that A naught F is equal to 0. In other words, there is no feedback. Well, then I just have 3 poles sitting on top of each other at a frequency of minus 1 over tau. The system is stable, right? And as I apply more and more feedback, you could see one pole, this pole in particular, keeps moving to the left, right? This term gets more and more negative. So one pole shifts to the left, and it's very stable. That's nice. On the other hand, the other 2 poles, you can see as I make A naught F larger and larger, this part becomes more and more positive, and so they shift to the right. So e to the j 60 means that they shift to the right with an angle 60 degrees. And so what I find is that my poles move on this trajectory, and at some point I can see that my poles actually move into the right half plane. So this is the left half plane, this is the right half plane, this is the j omega axis, and this is the sigma axis. Okay? So clearly, when they move into the right half plane is where things get interesting. So it's pretty easy to show, if you just look at this expression, that when A naught F is equal to 8, this is equal to 2, and this is then equal to 1, and I get purely imaginary poles. So the key point is that when A naught F is equal to 8, poles cross j omega axis. Okay, so right here, A naught F is equal to 8. Okay, so at that point, my first pole, my stable pole, is minus 3 over tau, and my unstable poles are plus or minus j square root 3 tau, exactly on the j omega axis. All right. So from linear system theory, we know that there's 2 kinds of responses. When you basically, there's a natural response and there's a forced response. In other words, if I take a transfer function, let's say in my case with 3 poles, I can always write this in the following form. Right? I could just factor this. And these three responses are basically complex exponentials. So the location of the pole tells me what kind of response I get from each of these poles. I know that if the poles are real and on a negative, then it's just an exponential decay. If they're real and positive, it's exponential growth. And if they have imaginary components, they ring and do the same thing essentially. So kind of loosely speaking, you can say that the output signal for this system has two components. One component, which is basically the natural response of the system, which we just talked about. And the second is actually a function of the inputs. So this is the forced response. And this is the natural response. Okay. Now the natural response is a strong function of the initial conditions of the system. In other words, initial charge on capacitors or an initial magnetic flux through inductors at time t equals 0, assuming we start our simulation at time t equals 0. Okay? So if you think back to the simulations you've done in SPICE, usually you're interested in the forced response. You have some kind of input, a stimulus, and there is a natural response, but if the circuit is stable, these things decay away, and after a few cycles, the forced response dominates. Okay? Most circuits that are stable are relatively low Q, so this really is the predominant response of the system. Okay? Think about a well-behaved, let's say, step response, right? A well-behaved step response has an exponential follow-through that follows the exact step response. A bad step response might be something that rings a lot. That ringing is due to this natural response that dies out. The rate at which it dies out depends on the quality factor of these natural response poles. So very high quality factor poles means the system will ring for a long time. Okay? So for instance, even if for a stable system, if we're looking at a step response, this is the input, the output might do something like this. This is nice and stable. On the other hand, a peaky system might do something like this. So it would ring. But eventually, it actually dies out. That's why it's a stable system. Now, the difference between this ringing and the unringing one is that maybe this stable system has a pole right here, whereas this system has a complex conjugate pole, let's say, relatively close to the j omega axis. Okay. Questions? Okay. So, as you guys are all aware, if you have a pole over here, it corresponds to a decay. Pole over here corresponds to growth. Pole over here corresponds to exponential ringing, but decay. Pole over here corresponds to exponential growth. So clearly, to build an oscillator, we need to put our poles over here, preferably over here. And of course, we know that the poles always occur in complex conjugate pairs. Okay? So we need some poles in right half plane to make the system unstable. Okay? So in our system that we just studied with the three initial poles, if we make the loop gain bigger than 8, so this is A naught F bigger than 8, then we apply feedback to our system. So here's the So somehow I feed back the signal and bring it back. As long as the net gain, which is basically the cascade gain here, times the feedback is bigger than 8, my poles are in the right half plane, and if I just turn on the circuit, what I find is that it will start ringing as follows. Okay. Now here's a good question for you. If there is no noise in the system, would this happen? Would you observe this amplitude growth? Anybody want to take a stab at that question? Yes? No? Okay. Anybody else want to refute that? Okay, that's a good point. If you're running a simulation, then the fact that you have round-off errors creates effectively noise. But let's say you had an infinite precision simulator. Oh, that's a very good point. Depends on the starting point, the initial conditions of the system. So if you have charge on these caps, then certainly there's energy in the tank to begin with, and you may see oscillation. But let's say there is no charge in the system. Let's say all I do is I have this system and I turn it on. There's no noise, there's no initial charge. Would it oscillate? Would it ring like this? Okay, well the hint I gave you guys is I turned it on, right? If you turn something on, that has a 1/s spectrum, right? A step response. And so that turning it on action has frequency components that excite the poles, right? So that's the key. You have to turn it on, and then it'll start ringing. Okay, so all we've done so far is demonstrated that this kind of behavior will happen. We still have no idea why the oscillations might go into a steady amplitude, why they stop growing. We have an idea that maybe it's related to the compression of the amplifier. Okay. All right, so this root locus plot has a nice frequency domain component. So in the frequency domain, I can plot the loop gain of the system as a function of, I can plot the frequency response as a function of loop gain. So for instance, if I had no feedback, I know that basically I have 3 poles right here, and so this would decay at 60 dB per decade. As I begin to apply feedback, interestingly enough, even if the feedback is positive, initially my system just becomes peaky. I apply more and more loop gain, the system becomes peakier and peakier, and eventually what I find out is as the loop gain approaches 8, so A0F goes to 8, this thing goes to infinity. So as A0F goes up, the response is peakier and peakier. Okay? Yes?
A0F being 8 is true only when you have a 3-pole system,
Yeah.
right?
Yeah, this is just for the case that we're discussing. Yeah. Thanks for bringing this up. So this is for our 3-pole system. Okay, so there's nothing magical about the number 8. Okay, so in particular, what's interesting now is we see that from a frequency domain perspective, at this particular frequency, there's infinite gain when A0F is equal to 8, which means that the system can regenerate itself. If infinity can always get into trouble, right? But for a moment, take your mathematician's hat off and say, okay, 0 times infinity is a constant. Okay, that's satisfying. That even though the system has 0 input, it has infinite gain, so it can have a finite output voltage. Okay, but that doesn't tell you what the output voltage is, right? Because 0 times infinity can be anything, right? It can be 5, it can be 100, it can be 1,000,000. So to find out what that amplitude is, linear analysis fails us. So we cannot predict the oscillation amplitude with linear analysis. We have to use some of our nonlinear analysis. Okay. Now, the way we're going to analyze this system is we're going to obviously have to make some approximations because it's a very complicated system. So what we do is we observe, first of all, that some oscillators that we build do go into steady state. Okay? So this is the steady state. This is the build-up. So for the build-up, we know that linear analysis is useful. Okay, because the signals are small. This transition region is very complicated. But the steady state behavior also has some simplicity to it. For instance, if we have a parallel LC tank, what we can assume is that no matter what nonlinearity we have in our circuit, if the quality factor of the tank is high enough, this voltage is sinusoidal. Okay? Now, if we're talking about an LC tank, series LC tank, we would assume the current is sinusoidal. Right? It's an approximation. So what I'm saying is I have an LC tank, and I have some nonlinear block here. That means that this nonlinear block can generate harmonics of my fundamental. But if the LC tank is good enough, most of the harmonic currents will flow into this capacitor. And so the voltage out here will be approximately sinusoidal, and then I can make use of the large signal sinusoidal analysis I developed when I looked at mixers. Right? So this is a simplified analysis approach, but it's pretty accurate as long as the circuit is pretty high quality factor. That's why at the beginning of the lecture I said sinusoidal oscillators. So we're making an assumption that our oscillators are pretty good sinusoids. Let me just stop there and see if that assumption makes sense to everybody. Okay. So the idea is that if this is the output voltage of my oscillator, then in steady state, it's a pretty good. And the reason I assume it's a pretty good sinusoid is that even though I have this nonlinear circuit here that can generate harmonics, the harmonics are getting shorted to ground by this capacitor. Okay? And if this is a sinusoid, then I know how a nonlinear circuit behaves to a large signal sinusoid. I can use Fourier series analysis. So for bipolar transistors, I know the current harmonics have a modified Bessel function response, right? So I can use that analysis and apply it to the oscillator. Yes?
Why the nonlinear term is represented in current form in this parallel RC with LC versus voltage in series LC?
Because an LC tank likes to see a sinusoidal voltage, right? A series LC tank likes to see a sinusoidal current. It's just the harmonics are getting suppressed naturally here for voltage. The current waveform can be very nonlinear, right? I can have a square wave driving this thing, and the output, square wave current waveform, right? And the output will look pretty much sinusoidal. Okay, so this will be clear when we go through a design example. All right, so let's do that. Let's look at a simple LC oscillator, and we'll start out with a circuit that looks a lot like the first mixer that we looked at. It's a BJT-based circuit. So I have an LC tank and a bipolar transistor. I'm going to use the bipolar transistor to regenerate the oscillation. So what I'm going to do is I'm going to take the output and drive it back into the input, and as good circuit designers, we're going to bias this with a fixed resistor value, emitter degeneration here, and we'll bypass it to get more gain at high frequency. And over here, I can bias this up, let's say, with a resistive divider and a bypass cap. And you'll see that I'm using a transformer in two ways here. I'm using the inductance of the transformer as part of the LC tank. So this is a non-ideal transformer. And I'm also using the transformer to take the input signal and make it smaller by a factor of n. So I take a small fraction of my output signal, feed it back into this amplifier, get some power gain, and then dump power back onto the tank. It's key that I dump the power onto the tank at the right moment. If I do it out of phase, I make a stable system. If I do it in phase, I make an unstable system, right? So I need a phase shift. So I desire a phase shift of 0 degrees through net feedback network. So that means that going through the, by net, I mean going through the feedback network here and then the amplifier. Since this is a common emitter amplifier, I know it has negative 180 degrees phase shift, so I need to introduce 180 degrees phase shift in this transformer. Okay? Any questions about this basic LC tank oscillator?
So what's the margin under zero phase shift?
We'll talk about that. Yeah, we'll come back to that point. Depends a lot on the quality factor of the tank. All right. Just to actually let me address that question now. We'll come back to it again. Well, let's say that you guys all know that no transistor is going to give you perfectly 180 degrees phase shift, right? There's going to be a few degrees of lag, right? All real systems have some delay, and so there's going to be a little bit of lag in this amplifier. That means that for the net phase shift of equal 0 degrees, the tank here, instead of working at resonance, should work slightly off resonance, where I can pick up some phase shift from the tank. Okay? If that doesn't make sense, hold on to that question. We'll come back to it. All right, so let's draw the AC equivalent circuit. So I have an LC tank, transistor, the emitter is grounded, and then I have an ideal transformer with n to 1 windings. So this is an ideal transformer. And this is actually the winding inductance. Remember when we talked about transformers, we discussed how you could take a coupled inductor, some mutual inductance like this, and transform it into an equivalent circuit like this, where this is an ideal transformer, and this is k squared L1, this is 1 minus k squared L1. So the idea is if k is close to 1, this series branch goes away, and I just end up with basically this winding inductance L1, which appears here. Okay. So L is the basically winding inductance, and RT is the effective tank resistance. Okay. So this is taking all the losses in the circuit and making an equivalent shunt resistor to represent it. So for instance, I know this LC tank, there's going to be a series resistance with this L because this winding resistance, right, that exists in the transformer. Well, I do a series to parallel transformation and move that into RT. Likewise, there are no perfect capacitors, although capacitors can be very good. Nevertheless, there's going to be some series resistance. I do a series to parallel transformation, lump that into RT. There's also output resistance in this transistor, right? Again, I'm going to take the output resistance of this transistor and lump it into RT. Now what makes this a little bit complicated is that series to parallel transformation is frequency dependent. So I have to have a pretty good idea what frequency I care about. Well, if this is an oscillator with an LC tank, that's defining the frequency. So it's somewhere around omega naught. Okay. All right, so let's analyze this circuit by just drawing an equivalent circuit. So I'm going to draw an equivalent circuit for the transistor. I'm going to make it pretty simple. I have a GM stage. I have my output resistance, let's say my output capacitance. Then I have some load resistance, which is due to the tank. Then I have my inductance. This feeds back into the input resistance and the input capacitance of the device. And let's neglect CMU as we do often in this course. So this would be GM V in. This would be the R out. This would be the C out. This is C load. Let's call this R load. And let's call this L load. Okay, so this is the equivalent circuit. The emitter is grounded. Observe that the forward gain of this amplifier, the forward gain is defined by breaking the feedback loop, injecting an input signal, and seeing what's at the output, right? So if there were no feedback in the system, that would be the open loop gain. The open loop gain is just basically apply a voltage here, get a current of GM, and that current flows into this tank. So it's GM Z tank at some frequency omega, right? So A of S is minus GM Z tank of S. All right? Where the tank impedance is basically a equivalent resistance, which is RO in parallel with RL in parallel with this input resistance transformed through the transformer, right? So this is N to 1 windings. Since the voltage drops across this resistance, it makes the resistor look smaller, bigger at this terminal. So looking into here, the resistance is N squared times R in. Okay. The tank capacitance, on the other hand, is C out of the device plus CL plus the input capacitance also transformed, which now transforms down by N squared. Okay? And the L of the tank is just the L of the winding that we discussed before, times K squared if you want to be a little more exact. Any questions about this simplified equivalent circuit? Yes.
GM in the circuit is also large variant signal that would be changed quite often.
Yeah, so right now we're doing small signal analysis, so we use a small signal GM.
Point would be changed so much because of feedback from the windings every time.
No, so we assume the bias point is fixed, right? So let's say that this is the original circuit. We find its bias point with RE, R1, R2, right? So the DC current would be this voltage roughly minus VBE over RE, right? That would give me IQ, and that's the quiescent point. Then I linearize about that quiescent point, and then I say, what if there's a disturbance in the circuit? What will happen? And the bias point, I'm going to assume, doesn't shift because I have this emitter degeneration and this large capacitor. So this capacitor tends to hold this voltage constant. This emitter degeneration also tends to reject changes in the current. Okay, so if this is the tank capacitance, this is the tank resistance, and this is the tank inductance, I can write the tank impedance as just a parallel combination. So it's 1 over SC, let's just call this SCT, plus 1 over RT, plus 1 over J omega, let's say SL. That's the equivalent tank inductance. Multiplying numerator and denominator, I have 1 plus S LT over RT plus S squared CT LT. And so that the loop gain, which is the forward gain times the feedback factor is therefore minus GM Z tank times 1 over n, where n is the transformer, right? And because I actually have a sign inversion through the transformer, I can write this as positive, right? So if I substitute, I get GM RT over N times L over RT times S, 1 plus S LT over RT plus S squared CT LT. Okay? And I can now identify this term as basically the loop gain at resonance, right? Because at resonance, the tank impedance is just RT, and basically the forward gain of the amplifier is a GM divided, and then n, 1 over n is the feedback factor. So this is the loop gain at resonance. All right, any questions? All right, so let me now write the total transfer function, H of S. H of S, just if I substitute for A f of S, my H of S, which is the closed loop transfer function, is equal to minus GM RT L over RT times S divided by 1 plus S squared CT LT plus S LT over RT. Should have never called these things T, should just call them L's and R's and C's. Minus 1 over GM RT over N. Okay? So the simple algebraic substitution of this into 1 over 1 plus A of S over 1 plus A of S F. Okay? So I can rewrite my H of S in the following form. Minus GM RT LT over RTS. So there's a 0 at 0. That's because I have a transformer. I can't do feedback at DC, so the loop gain drops to 0 at DC. And most importantly, I can identify this term as the loop gain. So this is 1 minus the loop gain. All right, so this is a very important form that I've put my transfer function in. Now, what's important about this transfer function is, first of all, let's assume that n goes to infinity. Effectively, that means there's no feedback in our system, right? That you're feeding back an infinitesimally small voltage. And so what happens to the loop gain is it just looks like a second order transfer function. It looks like a tuned amplifier. All right, this term goes away, and this is the quality factor of the tank, right? I can write this as omega over omega naught times omega naught LT over Q R, which is just Q. So I can put this into standard form. The denominator just becomes 1 over omega naught squared plus omega over omega naught times Q, for instance. On the other hand, what's more interesting, we're not interested in a tuned amplifier, we're interested in a feedback system. In a feedback system, the location of the poles is very strongly dependent on where we pick this loop gain. Most importantly, if this loop gain is equal to 1, this term goes away, and I have the transfer function for a system with 2 complex conjugate poles, or actually 2 imaginary poles. In other words, it looks like there's no loss in the system. So the most important case occurs, the observation loop gain equals to 1, the denominator just turns into 1 plus s squared ct lt. In other words, I have two poles on the j omega axis at plus j omega naught minus j omega naught, where omega naught is 1 over ct lt. And we know that if a system has poles on the j omega axis, the response is just oscillation with fixed amplitude. Right? So intuitively, we can imagine that our system, in steady state, from a small signal perspective, has poles on the j omega axis. Okay? We'll come back to that. Well, what I can do now is I can plot my transfer function, so the closed loop gain, as a function of frequency, as a function of loop gain. So this is for loop gain less than 1. This is my tuned amplifier. It has positive feedback. It's important to note that. And what I find is that as the loop gain basically gets closer and closer to 1, the response gets peakier and peakier, and as the loop gain goes to 1, the response actually goes to infinity. So here's the interpretation. I have this feedback amplifier. I've applied positive feedback on purpose. As long as the loop gain is less than 1, the amplifier essentially is still stable. And in fact, I can keep increasing the loop gain, but keep it less than 1. The system is still stable. The poles are still in the left half plane. But the response is becoming peakier and peakier. That's great. That's actually why people invented feedback in the first place, was to get more gain out of lousy vacuum tubes. Use positive feedback, but keep the loop gain less than 1. That's not, again, what we're interested in. We're interested in the loop gain either bigger than 1 or equal to 1. At equal to 1, we see the gain is infinite, apparently. Bigger than 1, we see that the poles actually move into the right half plane. All right, let's demonstrate that for a second order transfer function. So for a second order transfer function, let me just say 1 plus bs plus as squared. If I just basically find the roots of this, it's trivial. S12 is minus b plus or minus b squared minus 4a divided by 2. And let me write this as, let me actually now take the magnitude of this and assume 2a, thank you. Let me assume that I have complex conjugate poles. In other words, I can write S12 as minus b plus or minus j, 4a minus b squared divided by 2a. Let me look at the magnitude of these poles. The magnitudes would be b squared over 4a squared, magnitude squared, let's say, plus 4a minus b squared over 4a squared. And you can see that this term cancels out with this term, and so what I get is 1 over a. In other words, the magnitude of the pole is square root of 1 over a. And if I look at my transfer function, a, in this case, is equal to 1 over square root of LC. Actually, it's LC. In other words, the location of the poles is 1 over square root of LC. Okay? So again, drawing a root locus for this second order system, if I assume I have complex conjugate poles, what I've just shown you is that these poles are actually on a circle. So this is actually a circle. And what happens is as I increase the loop gain, these poles keep moving on this circle, and at loop gain equal to 1, they cross. All right? So loop gain now plays a very important role in the analysis of oscillators. Loop gain equals to 1 gives me, let's say, imaginary poles. Loop gain less than 1 gives me a stable circuit with more gain than possible without feedback. So it's positive feedback, it enhances the gain. Loop gain bigger than 1 gives me an unstable right half plane pole. Okay? So we've done small signal analysis for 2 circuits now. We did this 3-stage amplifier, and now we've looked at a tuned circuit, and we see similar behavior. Instead of poles moving on a trajectory of 60 degrees, here they move on a circle. And in general, any kind of, we've done 2 examples, but you can see some very general behavior. Any kind of system with positive feedback, if we increase the loop gain enough, it's going to move the poles into the right half plane. Okay? All right, so let's go to the next lecture. You guys aren't asking enough questions. Too late. No. Go ahead.
Can we in reality have an unstable circuit? I mean,
Yeah, right. That's, when you took 140, right? You build all these amplifiers trying to avoid unstable behavior. Some unstable circuits aren't that interesting. They just clip, right? You turn them on, and the output will saturate to VDD or VSS, and it'll stay there, right? In some sense, all digital circuits are also unstable, or they're metastable. So a digital circuit has a point where it's metastable, right? And then it has points where it's stable, either at VDD or VSS. So you actually will use that metastability in a regenerative fashion, let's say to build a flip-flop. So unstable circuits are very useful, definitely. Okay, so now we're going to do this steady state analysis, or we're going to start it. And again, the observation is that if we look at the current and voltage waveforms in our circuit, we're going to look at basically the output voltage. So the output voltage is going to do something like this. The input voltage is just going to be a copy. Basically, it's going to be this voltage divided by N. Same phase. So this is V out. This is V in, which is V out over N. And then, if this is V in, then we can calculate what the current is, IC. And IC of t, when the signal is small, will also, so this is, let's say, IQ, will initially look sinusoidal, but then as the voltage gets larger and larger, the behavior starts to look more and more like this. So this is basically the steady state is not sinusoidal. Okay? So the steady state current waveform can be very rich in harmonics, but we make the assumption that the steady state voltage is actually sinusoidal because of the high quality tank. So assume steady state output voltage is sinusoidal. All right? That means that the output voltage at any given time in steady state is just equal to the fundamental component of the collector current times the tank impedance at that fundamental frequency. And remember, we defined a large signal GM as exactly the ratio of IC omega 1 to V in. So this is GM times V in times Z tank at frequency omega 1. Okay. Any questions about that?
We get like we can reverse current versus voltage if we use a series LC tank. I mean, do
Yeah.
we ever use an LC tank to make an oscillator? Or
Sure, you can. Maybe we'll give it to you as a homework problem. All right. Okay, so again, you'll see the approximation here. This is the key approximation. The output voltage is sinusoidal, so I just take the first harmonic of this current and multiply it by the tank impedance, and that's the output voltage. But based on the mixer analysis that we did, we derived the large signal behavior, the large signal sinusoidal behavior of a circuit. We defined the large signal GM. Okay. Now, if I now plug in the fact that the input voltage is just V out divided by N, I have an equation that says V out is equal to GM Z tank at frequency omega 1 divided by N times V out. And so for this to be true, that means that in steady state, GM times Z tank divided by N has to identically equal to 1. So this is the condition for steady state oscillation to occur. If all my assumptions are to be self-consistent, then GM Z tank over N has to equal to 1. So this is probably the most important conclusion, is that the steady state equation for the tuned oscillator. And of course you could interpret this equation. What is GM ZT over N? What's little GM ZT over N? Loop gain, right? So big GM ZT over N is the loop gain that takes the amplitude of oscillation into account. So it's the large signal loop gain. So it's the effective loop gain a large signal sees through the amplifier and feedback network. In steady state, the loop gain, the large signal loop gain, has to equal to 1. Okay? Now the nice interpretation is that, remember, for a second order system we found that when the loop gain is equal to 1, the poles are right on the j omega axis. So from the large signal perspective, the poles eventually migrate back to the j omega axis. Idea is that initially, if I start out with a loop gain bigger than 1, as the system goes into steady state, it likes to relax into a state with loop gain exactly equal to 1. Right? And that makes sense intuitively because the signal is not getting regenerated anymore. The amplitude is constant. So if a signal goes to the feedback network and comes back, it should be the exact same amplitude as it was before. Now the important conclusion is that the magnitude of GM-ZT omega 1 over N should equal to 1, and the phase of GM-ZT omega 1 over N should equal to 0 degrees. So these are two conditions to find basically the amplitude. Solving these two equations, I can find the amplitude and frequency of the oscillation. Let's call this equation B, A and B. So solve equation A and B to find steady state oscillation amplitude and frequency. Okay? Questions?
Question?
Yes.
Why can you ignore the higher order harmonics?
Who's out? Okay. Because of the assumption of height. Right? It all comes back to this assumption, right? I'm assuming that in steady state, this output voltage is sinusoidal. That sinusoidal output voltage generates a sinusoidal input voltage. That sinusoidal input voltage generates some complicated but periodic collector current waveform. I do Fourier analysis on that collector current waveform, right? And I find the fundamental, and by definition, the voltage at the output is just the fundamental of this current times the tank impedance. Okay? That's the approximation. And for this approximation to be self-consistent, we find this condition has to be true, which is also very satisfying, right? Because intuitively we understand what's going on. Intuitively, the steady state loop gain is going to 1, which tells us from a small signal perspective the poles are moving to the j omega axis. Okay. Now let me show you guys how you go about solving these two equations. The way to do it is to note that the initial loop gain of the system, which is Gm z tank over n, is bigger than 1, right? That's because we want the poles to be in the right half plane. On the other hand, the large signal Gm z tank over n is identically equal to 1 for steady state. So if I take the ratio of these two terms, I get that the loop gain is equal to the ratio of small signal Gm over large signal Gm. Okay? So this is a very important equation. So let me make a plot of this equation versus the input amplitude. Because remember, this is a function of B, right? Where B is the input divided by KT over Q. So what I'm going to do is I'm going to plot, let me plot the inverse. Gm over Gm is 1 over loop gain. It's less than or equal to 1. It's less than or equal to 1 because we know as the amplitude gets larger, the Gm tends to compress. The Gm gets smaller. So if I were to make a plot, I would find that the ratio of Gm over Gm starts at 1 for very small amplitudes. That makes sense. For very small amplitudes, I'm in the sinusoidal region, right? Small amplitude region, small signal analysis applies. But as the amplitude gets bigger and bigger, it drops, right? And so eventually, at some amplitude, this will drop to 1 over loop gain. And that is actually the amplitude of oscillation. Yes?
So from here, is that true that the more nonlinear the circuit is, the higher, the lower amplitude of oscillation? Is that?
Not so. If this curve drops really fast, you're right. The interpretation would be that to get to a certain loop gain, you actually need a smaller input amplitude.
So what if for a square law device like MOS devices, they don't have a third term per se, they have no gain compression?
Very good question. Yeah, we'll talk about that next lecture. So real MOS device, if it's a perfectly square law, does not compress. You're right. So this curve actually would have gain expansion. It would go up. But in reality, as the amplitude gets larger, the device goes into triode. As it goes into triode, it compresses severely. All right, that's it for today.